In this second part, we will discuss the example of plane truss problem. In this example 1, we want to solve the unknown degree of freedom of this truss structure, where it has been loaded with a horizontal load 20 kN and a vertical load 10 kN at node 3. It also has been pin supported at node 4 and node 1, and it has a pin roller support at node 2, where it's allowed to move in y direction, either upward or downward. The first step that we have to do is to sketch a finite element model of the whole truss structure, labeling all nodes and elements, and indicating the status of all boundary conditions, which is to state that how many degrees of freedoms that we have to solve, as well as to label the relevant loads and reaction forces that will make our calculation easier later on. So in this case, let's see at the node 1. At node 1, he has been pin supported, meaning that node 1 cannot move in x and y direction, or in other words, cannot have a displacement in x and y direction. That's why u1 is equal to 0, v1 equal to 0. As it cannot move, of course, node 1 will have reaction forces. So that's why we have reaction force in x direction as well as reaction force in y direction. Let's move to the node 2. So in node 2 is a pin roller support, meaning that it still can move in y direction, or it can freely has a displacement in y direction. That's why v2 is unknown here. While for x direction, it's been supported, meaning that it cannot has a displacement in x direction. So that's why we put u2 is equal to 0. So once u2 equal to 0, meaning that it's going to have reaction force in x direction. While at node 2, we do not have any applied loads. That's why F2 in y direction is equal to 0. At node 3, this point is a free point. So when it's a free point, meaning to say it able to have displacement in x and also in y direction. That's why u3 is unknown, v3 also unknown. And at node 3, it has been loaded with horizontal and vertical loads amounting to 20 kN for horizontal load and 10 kN for vertical loads. And lastly, at node 4, again, node 4 is a pin supported, meaning that it cannot have displacement in x and y direction. So that's why u4 is equal to 0 and v4 equal to 0. Remember, when there is a restriction of movement, then we will have the reaction forces. So that's why at node 4, we have reaction force in x direction and reaction force in y direction. So in general, in this problem, we only has 3 degrees of freedom, which is v2 here, u3 and v3. The second step that we have to do is to determine the stiffness metric for each element by using this stiffness metric for a truss member that we have defined in part 1 of this lecture. The next parameter that we have to define is the material properties as well as the cross-sectional area. For example, in this case, all the truss members are made from the same material and having the same cross-sectional area. Those parameters are important to calculate the K matrix here. So in order to determine the stiffness matrix for each element, I really encourage you to draw a table like this so that we can list down all the important parameters that we need in order to determine the K matrix. For example, the first parameter that we have to define is the element. For example, in this case, this element has been provided to us, meaning that element 1 is for this member, element 2 is for this vertical member, and element 3 for this member. Let's say in the exam, this element has not been provided, meaning that you have to choose by yourself. You can choose any members to be your first, second, and third element. It doesn't matter. Okay. However, I really encourage you, when you want to numbering your elements, always follow the sequence of number or sequence of ABC, so that you won't confuse when you want to assemble in the global stiffness matrix. For example, in this case, we start our first element that having the first node here. Okay, that's why we decide element 1 is the one that having node 1. Okay, the next parameter that we have to define is the element connectivity, or the nodes, how we connect those elements. For example, element 1, how we connect element 1, either is from node 1 to node 3 or node 3 to node 1. There is a difference that I will explain later. Okay, again, in order to decide the element connectivity, I always encourage to follow the sequence of number so that you can avoid confusion when you want to assemble the global stiffness matrix. For example, in this case, if I were you, I will choose the element connectivity is 1 to 3 for element 1. For element 2 is from 2 to node 3, and element 3 is from node 3 to node 4. I just follow the sequence of number. And the third parameter that we have to define is the angle or the theta. So as we decide the element connectivity is from 1 to 3 for element 1, meaning that for theta for element 1, we must determine at node 1. And the theta is defined from 0 degree until it reach or it meet the truss member here. For example, this is the truss member element 1. So the theta is defined from 0 degree until to that member. So in this case, the theta is equal to 30 degree. For example, let's say you decide to connect the element from 3 to node 1. Okay, from node 3 to node 1. Meaning that if you choose from node 3 to node 1, the theta will define from node 3. And it's defined from 0 degree until it meet that element. So meaning that if you choose node 3 to node 1, this will be your theta. Okay, it's not the same. Alright, so we continue with the second element. Second element, element 2, is from node 2 to node 3. Okay, so meaning that theta is from 0 until it reach to this element. So the theta will equal to 90 degree. While for the third element, it's connected from node 3 to node 4. So from node 3, from 0 degree until that element. That will be the theta. So in this case, if you solve this theta, we will get 150 degree. The next parameter, once we have the theta, then we can determine all those parameters inside the K matrix, which is cos theta. Okay, in this case for element 1, cos theta, theta is 30 degree. So cos 30 degree is 0.866. Next parameter, we can define the sin theta. Okay, sin 30 degree is equal to 0.5. Next, we can define the c square that we need in this matrix. The s square again we need in this matrix, and the cos theta times sin theta, or cs. Cs also we need in this matrix. Next value that we have to define, as we have the E, we have the A, so the next value that we have to define is the length, okay, the L here. So for example, element 1, if you determine the length here, the length 1, okay, by knowing this length is 0.5, and here you have the angle, then we can obtain this length L1 by using the trigonometry with sign equation. So we can obtain the L for element 1 is 1 meter. So once we have all these parameter A, E and L, then we can calculate the K. I call it, this term here is K. Okay, so if you can, we can determine this value once we have all this value. So the K for element 1 is equal to 200 times 10 power of 6. You can, then we have to do the same thing for element 2 and element 3. So if you define for element 2, you will get all this value, and for element 3 you will get almost similar value to element 1, only different in terms of cos theta as well as the cs value. It's depending on the theta. Once we have listed down all the important parameters, next we can determine the stiffness metric for each material by using this equation. For example, element 1, we obtain this K matrix. So the first value here, 150, we obtain by multiply the K value here. So for example, element 1, we have 200 mega times C square. So in this case, C square is 0.75. So 200 times 0.75, then we obtain 150. The second value, we just need to refer CS. For example, CS, the value is 0.433. So 0.433 times 200 is equal to 86.6. And the rest will be the same method. How to define all this value? Just need to refer to this matrix. Okay, do not forget to name your columns and the row here as your reference later on when you want to insert in the global stiffness matrix. Please note that when we decide the element is connected from 1 to 3, so our column always start with node 1. For example, in node 1 we have U1 and V1, X and Y direction. So that's why in this K1, as we decide 1 to 3, so we have U1, V1, U3, V3. Similarly for the row, U1, V1, U3, V3. If you decide to connect the element from node 3 to node 1, then your column will start with U, U3, V3, U1 and V1. It depends how you connect the elements. That's why I encourage you to follow the sequence of number so that it's easier for you to insert in the global stiffness matrix later on. And the second element, and for the third element, by using the same method, okay, by using this matrix, by referring to this table, then you can obtain the K matrix for second element and the third element. Okay, for element 2 is connected from 2 to 3, meaning that the column started with U2, V2, U3, V3. While for element 3, as we connected it from node 3 to node 4. So it starts with U3, V3, U4, V4. The same case for the row U3, V3, U4, V4. Next step is to obtain the global stiffness metric for the whole structure. We have defined the K matrix for each element. Now we need to combine all these metrics to become one global metric for the whole structure. Okay, so what we have to do, we just need to insert the matrix element by element. For example, we want to insert element 1 first into the global matrix. In the global matrix, we have to define all the columns in the structure. So in this case, we have 4 nodes. So we have U1, V1, U2, V2, U3, V3, U4, V4. Okay, we have to define all the columns. So we just need to insert this matrix according to its position. For example, here we have 150 is at U1 and U1. That's why we insert here U1. Okay, U1 here 150. For example, you want to insert U3, U3 here. So U3, U3 150. So you have to check U3 here, U3. Okay, 100, 150. Okay, for example, V3 and V3. V3 and V3 is given by 50. So check in this matrix. V3 and V3 is here is the position. It's V3. So just follow the position. That's why it's very important to define this row and this column. Okay, so you need to define this column as well as the row number. So that is easier for you to insert in the global stiffness matrix. Next, we want to insert the second K matrix, which is for the second element. We insert the second element into global matrix. Is represented by the blue color. Okay, and then in this second element, it started from V2 and V2. So check V2 and V2, we have 400 here. And then next is this one value, V2 and V3, which is negative 400. So we have here V2 and V3 here, negative 400. Next is V3 V2. So V3 V2 here we have negative 400, and the last one is V3 V3. So V3 V3 we has 400 here. So whenever we have overlap, we just need to plus. Next is to insert the third matrix. Okay, for the third element. Alright, so we insert the third element. Is represented by the green color. Okay, and then it started with U3 U3. So check U3 U3, we have 150 coming from the third element. So when we have overlap, just need to plus. And then the second value is U3 V3. U3 V3 is negative 86.6. So check U3 V3. So we have negative 86.6. Okay, that's how we insert the matrix according to its position. For example, we have V3 U4. For example, here V3 U4 is given by 86.6. So check in this global matrix V3 U4. V3 U4 is this value. So we have U4 and V3. So we have this value, for example. It's not very difficult to insert the local matrix into global matrix. Just need to follow its position. Okay, the column and row number. So once we have all these values, next we just need to solve all these overlap values here. Okay, we just need to solve all these value to have a single digit. So by solving that, so we obtain our global stiffness metric for the whole structure. Okay, at the column and row that we don't have any value, so we just need to replace with 0. The next step is to apply the boundary condition to our global stiffness matrix. In fact, we have defined this boundary condition in our first step. So we just need to recall back. In our first step, we have defined that U1, V1, U2, U4 and V4 is equal to 0 because all these points, all this displacement has been supported by the boundary condition. Okay, so next we just need to apply this boundary condition in our global matrix. So for example, U1 is equal to 0, okay, meaning that the row and column for U1 we can eliminate because it's no more useful for us because the value is already known. So we can eliminate the row for U1 as well as the column for U1. Similarly, we do for V1. We can eliminate the row for V1 and the row for V1. And next we can do the same for U2, U4 and V4. So that we only has a 3 times 3 matrix here. The active value that has not been slashed. Okay, so we have this 3 times 3 matrix so that we can take it out this matrix in order to solve for the unknowns. So the next step is to set up the system linear equation, which is F equal to KU. So this matrix, okay, we obtain from the global stiffness matrix. Alright, and then U, we know that U is the unknown displacement that we want to define. Now we have to define the force for each of these unknown. For that, you have to refer back to your step 1. Okay, in the step 1, we have defined all these forces. Okay, for example, for V2, so check V2 here, the force is equal to 0. While for U3, okay, in U3 we have defined that F3x is equal to 20 kilonewton. So you just need to replace with 20 kilonewton here. While for V3, we have defined F3y is equal to 10 kilonewton. Okay, for V3 is 10 kilonewton. Once we have this, next step just to solve the unknown degree of freedom by using the calculator, or you can use the Gaussian elimination method. It's up to you. But the easiest way is to use your calculator by using the equation mode of 3 unknowns. Okay, this is just an optional. For example, if you want to determine the reaction forces that occur in this system, because we have a pin supported. So when we have pin supported, of course, we're going to have reaction force as shown in this figure that we define in the step 1. So we have reaction at node 1 in x direction, okay, reaction force in y direction for node 1, here also for node 4 in x and y, and then node 2 we have reaction in x directions. So if you want to define all these reaction force, what we have to do is we need to use back our global stiffness matrix. Okay, those lines or the row that we have eliminated, we can use that row to calculate the reaction force. For example, the first row U1, okay, we can use that row to calculate our reaction force in x direction. Okay, because U1 is RF1x. Okay, and for V1 we have RF1y. Okay, for the second row. The third row is for U2, which is RF2x. For the second last row is the U4, is for RF4x, and the last one is V4 RF4y. So in order to determine this reaction force, we just need to multiply with those that are having displacement. For example, in this case, we know that U1, V1, U2, U4 and V4 is equal to 0. So wherever the value here multiply with 0, okay, will equal to 0. So what you have to do, just need to multiply the values in this row with the one unknown that having value. For example, in this case, we have V2, U3 and V3. So that's value we can use or we can obtain from our results displacement, okay, in the previous step, right? For example, in RF1, okay, so 0 times V2 is 0. Here we have 150 times U3 minus 86.6 times V3. So by replacing this value into this equation, then we can get the answer. Okay, the same thing is for RF1Y. Okay, so we have a negative 86.6 times here U3 and negative 50 times V3. So that's why we have this equation. RF2X, so in this case all these value are 0, so that's why we obtain 0. RF4X, okay, check RF4X, so we have here 150 times U3 plus 86.6 times V3. Okay, that's why we have this equation. And the last one, so we have 86.6 times U3 minus 80 times V3. That's why we have this equation. So in order to solve this reaction force, we just need to replace those value into these equations. In this slide, I would like to do some reflection on the global stiffness matrix. What you have seen so far on those columns that having zero displacement. If you notice, those columns are not useful at all in any calculations. Either we want to solve for the displacement or for the reaction force, because whatever the value here multiply with 0 will always equal to 0. Okay, so meaning that it's not useful at all. From this reflection, actually we can simplify the calculation method by eliminate these columns since the beginning, meaning that when we want to determine for the K matrix for each element, we can already eliminate those columns. For that example, please refer to part 3 of this chapter.